we go. Peptides and proteins are polymers of amino acids. I'm going to abbreviate amino acids as just AA. Peptides generally have, and it's kind of murky as to when a peptide becomes a protein. Peptides generally have, we'll say, less than 50 amino acids. Proteins have, maybe greater than 30 amino acids. So there's some overlap in there, and there's not really a good defining line between the two. Most of the proteins that are important, most of the peptides/proteins that are important in biology are quite large, though there are a number of very important peptide hormones: insulin, oxytocin, vasopressin, and others. So just be comfortable with using those words interchangeably. So we are going to talk about the 20 amino acids, and I am going to ask you to learn their structures, especially their side chain structures. But first, I want to take you on sort of a tour through protein conformations and secondary and tertiary structures. So first, I'm going to draw a section of a peptide within a larger protein. The peptides and proteins in biology are composed of what are called alpha amino acids. And the reason they're called alpha amino acids is because the amino group is attached to the alpha carbon. And so just like we did with carbonyl chemistry, we're going to continue to talk about carbons along the peptide chain. This is the carbonyl carbon, this is the alpha carbon, and then we'll call this the amide nitrogen because it's tied up in an amide with the next amino acid. Squiggly line here means there's another amino acid here that we're not drawing. And this alpha amino acid with a side chain, which we're not saying what it is, will be bonded to the next one, and so on. So you can draw sort of a repeating peptide chain in this way, and you've got each subsequent amino acid thereafter with a side chain. And notice that the stereochemistry of the side chains is all the same, and that is because biology makes proteins from what are called L amino acids, and that's a throwback to an old way of talking about stereochemistry, L and D, which had to do with left versus right hand rotation of plane polarized light. So you'll hear people talk about the L amino acids. Shoot, that eraser's too big. And what they mean by that is just the natural amino acids that nature uses. In reality, we're going to see if we use the typical stereochemistry that you're used to. Most of the amino acids have the S configuration, except one of them, which is R, but really only on a technicality because the priority of a sulfur in its side chain. So I'm going to just highlight the individual subunits, the individual amino acid subunits in this peptide that we're drawing. People will call each amino acid within a protein, they'll call it a residue, which an amino acid residue, which is kind of weird, and I'm not sure where that nomenclature really comes from, but it is what it is, and so you'll hear me talk about amino acid residues within proteins. So just be aware and ready to know what I'm talking about. You'll hear biochemists point to an amino acid and say, this residue does whatever. All right, so here are the individual amino acid subunits of our peptide. And you'll notice the thing that connects them is an amide bond. So let's focus in on the bond between the purple nitrogen and the orange carbonyl. And we'll just maybe highlight that, in gray. All right, sometimes people call this, of course, the functional group is an amide bond, but sometimes people will call that a peptide bond. And those terms are used interchangeably. By the way, the first time I ever heard the word peptide, I remember I was maybe 10 or 11, and it was on an episode of Star Trek The Next Generation, where Lieutenant Worf, where actually, no, it was Data was having strange, weird dreams, which androids dream, but and in his strange dream, Lieutenant Worf was eating a cake, and he said it was a mint peptide cake. And that, now in retrospect, makes absolutely no sense. They were clearly just mixing and matching technical sounding words, but that's the first time I ever heard the word peptide. And now this is what I do research on, so it's kind of fun. All right. Let's see. The important thing to remember about the amide bond is that rotation is somewhat restricted about that amide bond. And the reason for that is resonance. You expect both the carbonyl carbon and the nitrogen to be trigonal planar and sp2 hybridized because of resonance. So for an amide bond like this, we can draw a resonance structure where lone pairs on the nitrogen donate into the carbonyl carbon, and we move the pi bond on from the carbonyl out onto the oxygen. And in order to take advantage of this resonance stabilization, these atoms, the oxygen, the carbon, the nitrogen, and the proton, are all going to be in the same plane. Okay? Actually, the idea that resonance is what makes this happen has become somewhat controversial, but we're going to stick with the explanation because it's pretty simple. All right. Yes?
Could you scroll? That little box is like right in the way.
Oh, thank you. Sorry.
Thank you.
All right. Guess what's behind the box, right? Okay. Other questions? See the hand? No? Okay. So sometimes when talking about secondary structure in peptides and proteins, we want to talk about the position of two different amino acids in relation to each other. And so this is kind of brainless and not that interesting, but I think I'm going to use it in the coming in the next few minutes. So I want to say you choose any amino acid that you want as your reference point, and you call it the I position. And then this one is I plus 1. And then the next one is I plus 2. And if you can count, you're good at this point. You already sort of know where we're going. I plus 3, I plus 4. And if you're Count Von Count from Sesame Street, this is very exciting. But the reason we do this is because in regular secondary structures, there are specific interactions that between amino acids that occur with regular spacing. So for example, in an alpha helix, we'll see a key interaction between the I position amino acid and the I plus 4 position amino acid. All right. So let's talk about conformation, because these chains of peptides need to fold into particular shapes in order to do the chemistry that enzymes do. And so let's talk about which bonds you can rotate around. You can rotate around the, let's see, what color do we want for that? I don't know. Blue. You can rotate around the bond between the nitrogen and the alpha carbon. You can rotate around the bond between the sigma bond between the alpha carbon, and the carbonyl carbon. And then you can rotate around the bond between the carbonyl carbon and the next nitrogen. And as we've said, we expect there to be restricted rotation around that bond because of the resonance issue that we talked about. But we expect freer rotation around these two sigma bonds. Interestingly, though, this is not going to be like, I think in 351 you learned about butane and ethane. You learned about staggered versus eclipsed, gauche versus anti. But in those cases, the two atoms bonded to each other were sp3 hybridized. Here, you got an sp2 atom bonded to an sp3 atom. So the geometry is just a little bit different, and that can influence protein structure. Before, in 351, you probably learned about dihedral angles, and which is just looking down the bond that you're rotating around, choosing some reference points, and measuring how far apart they are. But in peptide and protein chemistry, we name these dihedral angles because we can actually learn stuff about protein structure by analyzing them. So we call the dihedral angle about this bond between nitrogen and the alpha carbon the Greek letter phi. And I don't know why we do that, but that's the letter they've chosen. For the bond between alpha carbon and carbonyl carbon, for the dihedral angle about that bond, we use the Greek letter psi. And then for the bond between carbonyl carbon and nitrogen, we use the Greek letter omega, phi, psi, and omega. And we'll talk about the values that are typically adopted by each of these angles and how that influences the structure that a protein has. Questions so far about all of this? Sort of boring nomenclature. I'm telling you this because I remember taking biochemistry, and I remember learning about phi and psi angles, but not really understanding them and thinking that it was basically pointless. But actually, it's sort of the key to understanding protein structure. So if you've ever been told in a class, yeah, we don't really understand protein folding, we really don't understand how sequence leads to folding, tell that to Google's artificial intelligence AlphaFold, which can predict protein structure based on sequence, but also tell that to all the peptide and protein chemists who know some of the rules for protein folding, and it has to do with these phi and psi angles. So this is going to allow us to open the curtain and peer behind the sort of secret box of protein folding to see what's going on. One other thing is that peptides have directionality. Notice that the side chain the backbone of the peptide goes from nitrogen, nitrogen, alpha carbon, carbonyl carbon, and again, nitrogen, alpha carbon, carbonyl carbon, and so on. So one end of the peptide is different from the other. We will call this end of the peptide where the nitrogen is the N terminus, and we will call this end of the peptide the C terminus. Sometimes people get mixed up. If you want to use this term, this noun, N terminus, as an adjective, this is a grammar class, you can use the phrase N-terminal as in an N-terminal amino acid. But you don't talk about the N-terminal of a protein, because then somebody's going to say, the N-terminal what? So it's the N-terminus of a protein or a peptide, the C-terminus. If you want to use it as an adjective, you use the terminal. That is actually a pet peeve. I'm sorry I'm subjecting you to that, but it bothers me when people say, use the adjective as a noun. Okay. What else? Have I talked about backbone versus side chain? The nitrogen, alpha carbon, and carbonyl carbon, and really the carbonyl oxygen, are all sort of backbone atoms, and then the R groups are the side chains, which we'll talk about later. So what we're going to do now is I'm going to show you an image of a protein secondary structure. So what is shown here is 3 alpha helices that are packing around a single axis. We'll talk about how this happens. This is a structure called a helix bundle or a coiled coil. But for excuse me, right now, I want to show you how this alpha helical structure. This is so important to me. I'm getting emotional. I'm really not. I just have a hoarse voice. Anyway, I want to show you how this long-range sort of spiral structure is really determined by the phi, psi, and omega angles that I showed you before in a peptide. So we're going to take this structure and we're going to zoom in on these 3 amino acids. We're going to call this one the I position amino acid. This is the, I plus 1. And in green will be the I plus 2. All right, and we'll go ahead and copy the first few residues of our peptide. We can redraw it because that's just too busy. So this will be the orange amino acid with its side chain. This will be the purple amino acid with its side chain. And this will be the green amino acid with its side chain. Orange, purple. I know that drawing in color is taking up time, but actually I think it makes it easier to see. So we're going to stick with that. And we're going to focus in on the dihedral angles for this central amino acid. So about rotation around this bond is going to be omega. Rotation around this bond is going to be phi. That's the dihedral angle. And rotation around this bond is going to be psi. Okay. So let's zoom in on this bond between carbonyl carbon and amide nitrogen. And to do this, I have taken this 3D structure. It's a crystal structure of a molecule we work on in my lab. And we're going to zoom in on this portion. And then what you're seeing here is the carbonyl carbon and the alpha carbon and the nitrogen for and then this is the R group for the I position amino acid. And then you're seeing here the nitrogen, the alpha carbon, and the carbonyl carbon for the I plus 1 amino acid. And we're going to look down the bond between carbonyl carbon orange, the orange carbonyl carbon, and then the purple amide nitrogen. And we will, like we usually do, use our evil Sith eyes to do that and look down that bond. So if we do that, and I realize that you cannot draw this in your notes, okay? So this is going to be available online. But I felt like it was better to show you the actual structures than to try to draw them myself. So we're looking down the carbon-nitrogen bond. From this perspective, in front is the carbonyl carbon. Here is the oxygen. Here is the alpha carbon. In back, where you can't see it, is the amide nitrogen. Up here is the alpha carbon, and down here where you can't see it is the amide proton. Okay. So this dihedral angle is going to be defined as the angle between the orange alpha carbon in the front and the purple alpha carbon in the back. Just going to measure that angle. And as you can see, it's 180 degrees. All right. Which is what we predicted, right, for a planar amide bond. So in the alpha helix, all of those bonds have that dihedral angle of 180 degrees. All of those carbon-nitrogen bonds between carbonyl carbon and amide nitrogen have that dihedral angle of 180 degrees. So that's one bond rotation that that we can define, and usually we'll see in peptides and proteins omega equals 180. Sometimes omega will equal 0, which would have the two alpha carbons eclipsed with each other. All right. Questions so far? The shape that we're looking at, sometimes people will talk about amide bonds in old stereochemistry terms. For example, with the 180 dihedral angle, we'll call that a trans amide bond because the alpha carbons are on opposite sides. And then for when omega equals 180, we'll call that a cis amide bond. Okay. So now let's look at phi, and that is going to be looking down the bond between the orange, let's see, nope, I'm wrong. Phi is going to be looking down the bond between the purple amide nitrogen and the alpha carbon. And coming off that amide nitrogen, you're going to have the amide proton, and you're going to have the carbonyl carbon of the previous amino acid. And then in back, you're going to see the attached to the alpha carbon, you're going to see the alpha proton, the carbonyl carbon, and the side chain. And this is the side chain group for the purple amino acid. We'll talk about what it is. It's actually a benzene ring. But let's just get oriented and let's put and again, you know, guys, I got totally fooled the other day. I had a student in my office, and we were talking about the new upcoming Obi-Wan Kenobi series, and we searched for a trailer, which we found, but it was fan film, not the actual thing. So I was really very disappointed. Okay, so we're zooming in, we're looking down that bond. So just to orient you, again, right here in front is the amide nitrogen. In back, where you can't see it, is the alpha carbon. In back, this is the alpha proton, and this is the carbonyl carbon. And then in front, we have the amide proton and the carbonyl carbon of the orange amino acid. The relevant dihedral angle here is going to be between these two carbonyl carbons. That's the angle phi. And in an alpha helix, that angle tends to be around minus 57 degrees. There is a sign convention, by the way, but you don't need to know it. Go ahead.
Isn't the Sydney supposed to be looking at the...
Oh, yes, thank you. Some of you were muttering in confusion. I appreciate that. Yes, the evil Sith eye is supposed to be right there looking down that bond between nitrogen and alpha carbon. Sorry. Okay, what else? Dihedral angles it's basically vector math. The two vectors that you're working with are the nitrogen to carbonyl carbon and then the alpha carbon to carbonyl carbon. You measure the angle between two vectors. It's I can't remember whether it's the cross product or the dot product or something. But anyway, that's how you do it mathematically. And the sign comes out from that. There is a sign convention whether one's on the clockwise versus counterclockwise side, but we don't care about that. So in an alpha helix, most residues tend to have angles that are in this region, around minus 57. And then if we do the same thing for the last angle, the psi angle, that's going to be looking down the bond between purple alpha carbon and purple carbonyl carbon. On the purple carbonyl carbon, you're going to see the oxygen and the nitrogen of the next amino acid. So I guess that would be the green nitrogen. And then on the alpha carbon, of course, you're going to see the alpha proton, the purple nitrogen, and the side chain R. Notice actually that the angle that's adopted here for phi, I didn't point out the side chain, but the side chain is eclipsed with the amide nitrogen, which may be as good as you can do here. And you might imagine that the size of the side chain might influence this dihedral angle. And so we will see there are some side chains that are more tolerated in alpha helices than others. Some work better than others. And it has to do with whether if by adjusting this angle we can relieve steric problems with this large side chain. All right, sorry, looking down the bond between alpha carbon and carbonyl carbon, and again, I'm not going to redraw it, we'll just paste it. Oh, it doesn't want to paste, okay. I made the mistake when my kids were younger, well, when Adam was younger, of watching The Revenge of the Sith, which is, I guess, sort of scary. And Adam sort of doesn't like Star Wars to this day, I think because he hates the part where Anakin looks at Obi-Wan and says, "I hate you." I'm like, everybody hates that part, but it's not because of that, it's because of the acting, right? So looking down the bond there, here's the sort of Newman projection view. Here's your amide nitrogen in front, the carbonyl. Oh my goodness, guys. Here is the alpha carbon in the front. The carbonyl carbon is in the back. Here's the alpha proton. Here is the side chain. Here is the nitrogen of the purple amino acid. And then in the back, you've got the oxygen and then the nitrogen of the next amino acid. And the dihedral angle that we're going to care about here is the angle between those two nitrogens, and that is what we're calling psi. And in this alpha helix, psi tends to be also negative and about 47 degrees. Okay. So yeah, we're looking at the angle between those two lines. So in an alpha helix, yeah, go ahead.
I would say I did like working down the bonds, but how do you know which atoms to compare through the angle?
How do you know which atoms to compare through the angle? It's a convention. I mean, what do I mean? Just as with nomenclature, there are rules. The angle psi is defined as the angle between the two nitrogens. And similarly, the angle phi is defined as the angle between the two carbonyl carbons. So you focus on backbone atoms. I guess that's the principle. And I'm not going to be asking you to measure dihedral angles because you would just sort of guess, but I want you to understand that these angles govern the shape of the backbone and what path it traces out through space. Do I see a hand? Yeah.
I was just going to ask, what's the definition again of
The dihedral angle omega is also between backbone atoms. It's alpha carbon in the front to alpha carbon in the back. Yeah.
Okay, so sorry, I'm still a little confused. So, like for example, with psi, you told us earlier that it's the alpha carbon to the carbonyl carbon. So
That's right.
The bond that we're looking down.
That is the bond we're
And
looking
then
down.
you
Yep.
compare the two amides.
That's right. That's right. We look down the bond between alpha carbon and carbonyl carbon, and we compare the two bonds with the amide nitrogens. Yeah. I saw another hand here. No? Yes? Anybody? Bueller? Yeah.
So, like, I don't want it to be one of those questions where, like, oh, how would it show up on a test? But, like, if, like, we were, like, asked about it.
But how would it show up on a test?
Like, we just need to identify, okay, we're given an image, we can find the atoms in the backbone. Would we identify the angle that it is?
I don't know that it would. I mean, I have asked questions on this stuff before on a test, but I'm not that interested in memorization, so I don't think it's that useful for you to memorize that in an alpha helix, the angles are minus 57 and minus 47. So maybe I'll have a better answer for you on that later. I sort of need to check what I've done. I think it's fair enough to ask you to know the definitions of those angles, but I'm not sure. That's an unsatisfying answer, and I'll be able to answer that more once I prepare your study guide. By the way, I know I'm behind on study guides, and that's fine. It is what it is. We've already gone through Chapter 22. I can write a study guide for Chapter 22, which I think would be useful for you, but I will go ahead and give everybody all the points for that study guide because I'm late. And then you will find for these next sections that are more in the biochemistry area that we're going to use the text some, but then a lot of the other stuff is going to be things that I tell you in class. So you're going to have to rely on your notes a little bit more. And if there's anything you're confused about, just look at Wikipedia, which actually has a lot of this stuff on it too. Okay? You would be surprised. I think one of my skills as a scientist, one of the best things I know how to do is ask Google the right questions. Seriously, when people come to my office and ask something I don't know, I say, let's Google that. And I don't know. So don't be afraid to Google things to try to enhance your understanding. Anyway, if we look now at this section back in the alpha helix, and if we go through that process and measure all those dihedral angles in the way that we did for the purple amino acid, an interesting pattern emerges. So what we would see for these amino acids, if I sort of write a table with phi and psi values, and then do this for the I position amino acid, the I plus 1, and the I plus 2, we make the following measurements. And what I was giving you before for psi angles are sort of general guidelines for within an alpha helix. The actual numbers you measure for these amino acids are as follows. Please don't memorize these. We're just looking at data and trying to learn from it. Okay, so you see that there's some variation, but in general, they're in this neighborhood of around upper minus 50s and upper minus 40s. And when you have a string of amino acids that are connected to each other and they all adopt these dihedral angles, you just built an alpha helix. In fact, the alpha helical secondary structure, there are programs today that will analyze the structure of a protein and show you where the helices are. And what they are doing is figuring out what these dihedral angles are. So it turns out that in the mid to late 1900s, as crystallography, so if you've never heard of crystallography before, crystals have a regular pattern of atoms, and if you shoot X-rays through them, that regular pattern of atoms diffracts the X-rays. They get deflected by the electrons in the crystal, and you can, through math that I don't understand, look at the diffraction pattern and back calculate out what the structure of the crystal is. And people began to do this for proteins. So you can grow crystals of some proteins, which is a weird process in and of itself, but you can mount those crystals on a little loop and put that loop in an X-ray beam, and then that tiny crystal will diffract the X-rays, and then again you back calculate out what the structure of the protein is, and that's where we get our three-dimensional structures today. As that began to happen, people started to look for patterns in the phi and psi angles, and Professor Ramachandran was the first to plot these phi and psi values to get a sense for what types of structures that amino acids would adopt. So on this axis, we're going to put phi, and on this axis, we're going to put psi. These lines in the middle are the 0 points, and then let's say here is minus 180, here is plus 180. Those two are actually the same thing. And then here is plus 180 over on this axis. And it might help to sort of put minus 60 and minus 120 there, and do the same thing here, minus 120, minus 60. If you plot on this map of phi and psi values, if you plot where our 3 amino acids are, they show up. I don't really like my square, but whatever. They show up sort of right here. And actually, as more and more crystal structures were analyzed, they saw a lot of amino acids that adopted dihedral angles in this region. And because of that, they call this region of the Ramachandran plot that's centered around minus 57 and minus 47, they call that the alpha region, because this is for things that are in a conformation that's compatible with the alpha helix. So when you take biochemistry, they'll show you some of this, but what I want you to understand is the structure of the alpha helix is not some magical loop that just sort of happens and, oh, it's a pretty spiral. It comes from, excuse me, God, I'm getting emotional. It comes from the fact that all of the residues in that alpha helix are adopting specific dihedral angles about those bonds. And that's an organic chemistry principle, that rotation around carbon-carbon bonds and carbon-nitrogen bonds and so on influences the conformation of a molecule. So when you have an extended section of amino acids that all adopt these dihedral angles, you get this spiral pattern. This is a ribbon diagram where the cartoon ribbon traces out the trajectory of the backbone atoms, and you can see there's this spiral structure. It's actually right-handed. Spiral structures have chirality. The way you can tell whether a helix is right-handed is you take your right hand and you point your thumb from N to C, and then you curve your fingers around the direction the helix is spiraling. And if your right hand works, then it's a right-handed helix. And if your left hand works, it's a left-handed helix. All of the L amino acids, helices composed of L amino acids, are right-handed. Now, what about the one interesting thing is if we switched the signs on these phi and psi angles to plus 55 and plus 45 and so on, we'd have a region right here that would still form an alpha helix, but it would be left-handed. So that's an interesting observation. If you switch the signs of both phi and psi, you have a left-handed alpha helix. And you can make one of those, but you have to use D amino acids instead of L amino acids. So this is sort of a stereochemistry issue. If you switch the stereo center of the amino acid, you can switch its dihedral angle preferences. So here is a Ramachandran plot for phi and psi, only this contains points for tons and tons and tons of amino acids in proteins. Each dot represents a specific observation, and you need computers to do this, or a lot of people and a lot of slide rules. So what you can see is that the values of phi and psi tend to cluster in specific regions, and then there are other regions where there's hardly any examples at all. And what's up with that? And the idea is that outside where there's not a lot of examples, those are areas where if you adopted that particular conformation, you would have steric clashes between the side chain and some of the backbone groups. And you can actually make a model and twist things around and convince yourself that in a peptide, stuff's going to start knocking into itself if you adopt those dihedral angles that are not heavily populated. Those that are in this region tend to be in the alpha helical conformation. Up here are regions that tend to be in a beta strand conformation. Over here, though it's not noted, is amino acids that tend to adopt conformations that are similar to collagen, like it's like a polyproline type helix. And then over here, you have only a few amino acids that can adopt left-handed alpha helical conformations. That's weird, right? Because L amino acids make right-handed alpha helices, so what are these doing? And that turns out to be really important for protein chemists, and they've learned a lot of stuff about the amino acids that can adopt these particular side chains. All right, questions so far? Yeah?
So if we're able to plot the phi and psi angles, do we have anything for omega, or is it just not?
Do we have anything for omega? You could, in principle, make this a three-dimensional plot where you put omega on the z-axis. It might not be that informative, though, because omega is generally either 180 or 0. So you only have two options, and in most cases, it's 180. So what people do instead of worrying too much about omega is they will just make note of the few times in the protein where omega equals 0. Good. Others? Yeah?
So do you know why the amino acid formed like a smaller amount than the L?
So it's not that the D amino acid forms in smaller amounts than L. It's that nature, the proteins we have are composed of L amino acids, and if they're helical, they're going to prefer dramatically the right-handed conformation. I'll tell you, here's a clue. The amino acids that are over here have this dihedral angle, but in general, they're not in a helix. They just adopt that angle in another context. Because the preference for the L amino acids is to be in a right-handed helix. I'm not sure I'm explaining this well.
Are we going to learn why like that is?
We're going to learn that there's a few side chains that are flexible. So one of them we can understand now. One of the amino acids does not have a side chain. It just has two hydrogens. So this is the alpha carbon. This is glycine. You might expect, because glycine lacks a side chain, that there might be some phi and psi values that aren't going to be a problem anymore because you don't have that large side chain group. By itself, glycine does not have, is not chiral, and so you might expect that glycine could adopt both of these types of conformations. And if you look at glycine and look at the Ramachandran plot for glycine, you have basically a reflection on either side for the angles that it can adopt. So there are limited pockets where you can avoid steric problems, but because glycine doesn't have a side chain, those same pockets exist on the other side of the Ramachandran plot. Basically, if you reflect the Ramachandran plot through the middle, you've got the other handedness or the other stereochemistry. And glycine just happens to be flexible in that without a side chain, it can adopt both of those. So there are some types of protein structures where you need not several amino acids with a right-handed conformation, or with a left-handed conformation, but just one. Like in a turn, maybe you need one to be left-handed. And in many cases, glycine is that amino acid because it, of all of the 20, is most comfortable in that weird spot that the rest of the 20 can't get to. Okay, other questions? You overwhelmed a little bit? Sort of wondering how the heck, or I'm supposed to keep track of this? Go ahead.
Would proline be the opposite of glycine in terms of reactivity?
Would proline be the opposite of glycine in terms of reactivity? Yes, look at proline. This is an amino acid where the side chain actually ties back to the amide nitrogen. So this is a ring. And what that means is that the values of the values of phi for proline are restricted. There are some it can't get to because you can't break the ring. And so if you compare, say, the values of psi adopted by proline to those adopted by glycine, it's a much narrower range. However, the phi values, you can see proline adopts still a wider range of phi values. And that's exactly right. It's the cyclic constraint. And again, that's an OCHEM principle. All right. So at the beginning of next class, I will try to have a better sense for the kinds of questions I might ask about this. I have to go look at an old test first. But have a good day, and we'll see you Friday.
How much OCHEM do we use in biochemistry?